Welcome everyone to the temporal graph reading group for today. We are very glad to host Filippo from the European Commission (JRC), who will be presenting their recent work making temporal betweenness computation faster and restless in KDD 2024. And a bit more information on the speaker for today. So Filippo is a scientific officer at the Joint Research Center of the European Commission. His current work revolves around quantitative and qualitative analysis of multimodal transport networks to support European transport policies aiming at enhancing accessibility and reducing externalities. And he obtained his PhD from INRIA while being hosted at IRIF in Paris under the supervision of Laurent Venet and Pierre-Luigi and Nets. And the focus of the thesis was on temporal graphs and specifically exploring models and algorithms with potential uses in transportation networks and for efficient routing algorithms. So I will hand the mic to you, and thanks for the talk.
Thank you very much for the introduction and the opportunity to share this work with you. Work that's joint work with Pierluigi Crescenzi, who's a professor at Gran Sasso Institute in L'Aquila, and Laurent Vienot, who's a director de recherche at INRIA Paris. And so today I'm gonna talk about betweenness in temporal graphs and how to compute it efficiently. So I bet most of you are already familiar with temporal graphs and different models of temporal graphs, but as there are so many, I would say it's worth to spend some time on the model and making sure that we are on the same page with the type of model that we used in our work. So in our case, we have a fixed set of vertices, and we have temporal edges joining them. And here, each temporal edge is depicted as an arc with two labels. The first label is the departure time of the edge, and the second label is the travel time of the temporal edge. So for example, this temporal edge here from A to B with labels 2 and 3 means that we can leave node A at time 2, then it takes 3 units of time to reach B, which means we're gonna reach B at time 5. So on top of that, we also consider some weighting restriction on the temporal graph. And so basically we are bounding the time that is possible to wait in each intermediate vertex when we are traveling in the graph. And from an application point of view, this makes sense, I don't know, especially for transport networks, whether it is public transit networks or flight networks, or even when in certain type of models of epidemic, for example. So let me now give a bit more formal definition of this model of temporal graph. We are given a set of vertices, V, and a list of quadruples that we call temporal edges. We have U, which we call the tail of the edge, the node V, which we call head of the edge, and then we have the departure time tau and the travel time lambda of the temporal edge, and the arrival time is given by the sum of the departure time plus the travel time. In this case here, we are considering strictly positive travel time. So as far as I'm aware, so in this talk we are not exactly talking about learning on temporal graphs. No, we're gonna talk about more exact computation, exact algorithms, computing some measures. So we are working in a setting where we have full knowledge of the temporal graph, and we are executing some computation on the temporal graph while having full knowledge. So the set V and the set E of temporal edges are given as inputs for the algorithm that we're going to see. They are given through specific type of representation, but that's we're going to talk about it later. So let's see how we can navigate, let's say, explore a temporal graph. We have what we call a beta temporal walk, which is a sequence of temporal edges, such that for any two consecutive ones, other than the more classical type of constraints, so of course the tail of the second edge has to be the head, of the first edge, and the second edge has to depart later or at the same time as the arrival of the previous one, but it cannot also, the second edge cannot depart after beta units of time after the arrival of the previous edge. So here it's where it comes into play the waiting time constraint. And a beta temporal path is a beta temporal walk in which all vertices are pairwise distinct. So it is possible to generalize what I'm going to present today to kind of more flexible waiting constraints. So in particular, introducing a minimum waiting time instead of a maximum waiting time alpha, and also in a way that each temporal waiting constraint is tailored to each node in the graph. So let's give some examples here. First, here we have an example of what is not a beta temporal path, because here we are leaving node S at time 1 and reaching node A at time 2. And then the second temporal edge departs from A at time 6, which means that we are waiting 4 units of time in node A. And in this specific example here, the maximum waiting time is 2. So we are not satisfying the maximum waiting time constraints. On the other hand, this one is a beta temporal walk. So this time we still leave S at time 1 and reach A at time 2, but then we perform some kind of, let's say, temporal loop around A. So we leave A at time 2 to reach C at time 4. We leave C at time 4 and reach D at time 5. And then from D, we go back to A at time 6. And then we leave A at time 6 to reach D at time 7 and the target T at time 11, 8 plus 3. So in this case, all the waiting constraint is satisfied on each intermediate node, and we are passing through A 2 times. So this is a beta temporal walk. So there is this result from the literature that tells us that when we consider this type of constraint, even deciding whether there exists a beta temporal path between two vertices is already NP hard. So fortunately, this doesn't mean that it's the end of this line of computation, let's say, but we can, instead of focusing on beta temporal path, we can focus on beta temporal walks. As we will see in this case, the problem is not NP hard. We can solve it in polynomial time, and everything can be done smoothly, let's say. And this holds for many different type of problems involving this model with the waiting constraints, including centrality measure, which is what we are going to speak about today. So as we are speaking about betweenness measure, let me first remind you what is the definition of betweenness for the classical notion of graphs, of directed graphs. So without the temporal dimension introduced. Basically, informally, we can say that betweenness measures how often a vertex lies in shortest paths in the graphs. And so more formally, it is defined as the sum over all possible pair of the betweenness of a node U is the sum over all possible pair of source and targets of the ratio between the shortest paths from S to T that pass through U over the number of shortest paths from S to T. So when we move to temporal betweenness, it's kind of similar, the definition, and we want to kind of measure the same type of things. So we want to measure how often a vertex lies onto optimal beta temporal walks. So in this case, sigma star SUT and sigma star ST are the number of optimal beta temporal walks from S to T and the optimal walks from S to T that contain U. So it's key here to notice that so in the classic notion of a graph, we are speaking about shortest, while here we are speaking about optimal beta temporal walks. So this is a kind of a very big difference. So in static graph, we are used to, when we want to optimize a path, we are looking for the shortest. That's normally what is done. While when we are working with temporal graphs, there are many different criteria that we want to optimize. So, and then we will go through them. But it's important to notice that based on the type of criteria that we choose, the optimal walks are different sets, of course. And this means that also the temporal betweenness of the nodes that that is concerned is going to be different based on what we are working on. So let's see some examples of different optimality criteria. So here, for example, one is called sometimes in the literature foremost, which means that we want to minimize the arrival time of the path. And here, for example, among all the paths from S to T, this one in here in green is the one that has the minimum arrival time, which is 10 to the target. Another type of criteria that we might want to consider is minimizing the number of temporal edges in the walk, which is often referred to as shortest. In this case, it's possible to go from S to T with 2 temporal edges. Always mind that we need to satisfy the waiting time constraints. Or another classical criteria is to minimize the duration of the temporal walk, where the duration is defined as the arrival time minus the starting time of the walk. So for example, this walk here is departing from S at time 3, and it's arriving to the target at time 11. So the duration is 8. And another possible criteria that we might want to consider is minimizing the waiting time, defined as the sum of the time spent in each intermediate node. So, for example, here we are only waiting in one node, which is here we arrive at, okay, here it's in B, because in B we arrive at time 7 and then we leave at time 8, which means we are waiting 1 unit of time in B, while for all the other one we are taking the temporal edge as we arrive. So now that we define all the ingredients, let's say, to analyze the problem that we are talking about today, let me first give you some quickly some results from the state of the art. We have this result from KDD of 2020. So in this case, there is no consideration of waiting time constraints, which means that it's possible to work with temporal paths rather than temporal walks. And in this work, the authors focus on these two type of criteria: shortest, which is minimizing the number of edges in the path, and shortest foremost, which means that among the foremost paths, you consider the shortest. So among the paths with earliest arrival time, you are only interested in those that have the minimum number of edges. And they compute the betweenness, the temporal betweenness of all nodes in n cube t square, where capital T is the number of time instants in the temporal graph of distinct, let's say, time events as arrival or departure of temporal edges. Then this second result here, the authors are considering weighting constraints, so as we are doing in this work, and thus working with temporal walks instead of paths. And they managed to compute the betweenness of all nodes for all classical criteria, for example, the one that we mentioned just now, in n square capital M t square, where capital M is the number of temporal edges in the graph. And here we have our results from KDD 24. And basically what we managed to do is, when we consider weighting constraints and thus working with temporal walks, we can compute the betweenness of all vertices for all the classical criteria in NM, where M is the number of temporal edges. Yeah, again. So just to mention here, we don't have capital T as a parameter. Just a quick remark to see how capital M can be put in correlation to capital T. So in the, let's say in the worst case scenario in which we want to compare our results to this first one here, is when M is equal to n square T, which means that the temporal graph is a complete temporal graph that is repeating itself at each time step. Okay, so here I want to introduce the temporal betweenness of temporal edges rather than vertices. And the reason is that in our work we really focus on temporal edges. Let's say in the algorithm that I'm going to present, temporal edges are the main authors, let's say, while I think that's quite of a difference compared to previous work where vertices are more the center of attention. So here, in particular, given a source S, here we are defining the betweenness restricted to the source S of the temporal edge E. So again, is the in a similar way of what we do for the vertices. So it's the sum of the ratios of the optimal beta temporal walks that contain the temporal edge E from S to T, of course. So it's quite easy to go back from the temporal betweenness of the edges to the temporal betweenness of the vertices, as it's explained here in this formula. So basically, if we manage to compute the temporal betweenness of the edges, we are fine to go, and we solve the problem for the vertices. So here I want to introduce another tool that we used in our work, which is a way, let's say, to to have a very general algorithm, and which is able to encompass the computation for all the classical criteria and also different type of criteria that one might want to define. So in order to do that, we define what we call a cost structure, which is a quadruple where we have a set of costs C, a function gamma that assigns to each temporal edge a cost, an operation O plus that given to cost returns one single cost, and then we have a total order on the set of costs C. And to obtain the cost of a walk, we combine the cost of its edges by, let's say, recursively define the cost of a walk. So the cost of a walk Q is given by the cost of the prefix combined with O plus with the cost of the last temporal edge of the walk. So let's see, just to, before seeing an example, I want to give one more detail about this, as we have some restriction on the type of cost structure that we admit in our work. And this means that we require the cost structure to satisfy isotonicity property, which means that if we are given three costs C1, C2, and C, and if C1 is less, let's say, precedes C2, then when they are both combined with C, then the order is preserved. And the reason why we need this is that, let's say, for example, that we have two walks from S to U, walk Q and Q prime, and both of these walks can be extended by a temporal edge E. Then what happens is that if Q was better than Q prime, then when they are both extended, then we still have that Q extended with E is better than Q prime extended with E, when better means like having less cost. So let's see an example. I would say the most simple example is to model shortest temporal walks. So in this case, C, the set of costs is the natural numbers ordered in the usual way, and the function gamma assigns cost 1 to each temporal edge, and O plus is simply the addition of natural numbers. So what happens in this case, if we consider a temporal walk, let's say from S to T, the cost of the temporal walk is simply the combination of the cost of these temporal edges, which are all 1 in this case. So by adding them up, we obtain the length, so the number of temporal edges that are present in the walk. So this way we can also, for example, model the walks that have minimum sum of delays. It's sufficient to assign to each temporal edge as cost its delay. So for example, this edge would have cost 1, this edge would have cost 3, and this one would have cost 4. So then when we compute the cost of the walk, we simply are adding the delays. More tricky can be if we are dealing, for example, with the fastest walks, which are the walks where we minimize the duration of the walk. So in this case, we can define the set of costs as, again, as the natural numbers. Then we assign to each temporal edge its departure time as cost. O plus, we define it in a way that returns the first argument. And then the order on the cost is the opposite of the order on the natural numbers. So what happens in this case is that when we compute the cost of a walk, it's going to be the departure time of the walk, because the O plus operation always returns the first argument. So when we are combining all the temporal edges, we are given the cost of the first temporal edge, which is the departure time of the walk. So here I'm just reminding you that the duration of the walk is defined as the arrival time minus the departure time. And the point here is that we are interested in walks ending with the same temporal edge. Here we are like, when we are talking about optimal walks, we are interested in the set of temporal walks ending with a certain edge. So all these type of walks have the same arrival time. So when we minimize the cost, we are basically maximizing the departure time. And as the arrival time is just based on the last edge, and this one is kind of fixed, we are minimizing the duration of the walks ending with the same temporal edge. But more formally, when we to deal with this type of criteria, we will need to add something else to the cost structure, which is a target cost function, let's say, which takes a temporal edge and a cost and returns a cost which can be even from a different set, and has to satisfy, is basically non-increasing in the second argument in the cost. So it has to preserve the order. So if we have C1 less than C2, then when we apply this target cost function, the order is preserved. And for example, in this case of duration, this target cost function would simply use the arrival time of the edge and the cost, which is the departure time, and the return arrival time minus departure time, which is the duration of the walk. And so here I'm not showing them, but using this cost structure and target cost function, it's possible to model all the criteria that I mentioned before, and even more different type of criteria. For example, it's also possible to do like the Cartesian product of these cost structures, and this is also needed. For example, if we want to minimize the waiting time of the walk, we have to go through the Cartesian product of different cost structures. So just before moving towards the algorithmic part, I wanted to spend quickly some words about the way that the temporal graph is represented when we take it in input for the algorithm. And basically what we do is having two lists, ER and EDEP, which are two sorted lists of temporal edges. One is sorted by arrival time and one is sorted by departure time. And we believe that some of these assumptions that we made so far can be weakened. Let's say, for example, these two lists can be assumed to be locally sorted instead of having a fully list sorted by arrival time. We can just focus on preserving the order for edges that have the same that are arriving or departing from the same node. And this is especially true for the computation part of the optimal temporal walks. For that part, we are sure, but then for the second part of the algorithm, it's still not clear if we can work with this type of lists. While the same kind of approach can be said for temporal edges with zero travel time, so delay equal to zero. And but that's kind of more tricky to handle, especially when there are cycles of temporal edges with zero delay. They can complicate stuff quite a lot. So let me move to the overview of the algorithm. It's inspired by Brunelli's algorithm, which is the most classical algorithm to compute betweenness in static graphs. So in a similar way, we have a forward phase to count the optimal beta temporal walks. So we have to, given a source node, let's say, we need to count. So we have to find which are the optimal beta temporal walks and count them. And to do this, we will see how we use the two different lists that I introduced just before. Then we have an intermediate phase where we need to refine the output of the first phase, because here in the first phase, we are computing the optimal beta temporal walks that end with each temporal edge. So let's say given a temporal edge E, we will be able to find and count the optimal walks that end with that edge. However, when we are dealing with betweenness, the optimality that we are interested in is the optimality towards the target. So basically, we will need to refine the optimality that we obtain from the temporal that regards the temporal edges in the first phase to the optimality of the vertices. And then finally, we have a backward phase where we accumulate the dependencies in a similar spirit as Brandes, let's say. So knowing the betweenness of the temporal edges that are successors of E in optimal beta temporal walks, we can compute back the betweenness of the edge E. Here, but I will give more details in the next slides. I will try to explain these three phases through some, especially I will focus on the first and third phase and with some figures. So let's start here with the forward phase. So in the forward phase, we are performing a linear scan of ER. So ER is the list of temporal edges sorted by arrival time. Okay, so we are analyzing each edge by non-decreasing arrival time, and then whenever we are reading an edge E, we perform two different types of operation. So the first thing that we do, it's depicted here on the left. So we will consider, okay, so here comes into play the second type of list, the one sorted by departure time. But here, as you can see, there is an index U. It means that basically from the list sorted by departure time, we by bucket sorting, we get some, let's say, adjacency list for each node, which are the list of temporal edges departing from U sorted by departure time. Okay, so here we have the temporal edges that leaves U and are sorted by departure time. So we can find E because E has tail U. Okay, and here in this list we have some intervals here that are colored, and each interval, let's say it's a kind of a window of temporal edges in the list that has associated a cost and a number that is so the cost is the minimum cost that these edges is the minimum cost of the walks that these edges can extend, and this is the number of such walks. Okay, so for example, here we have an interval from L1 to R1, which means all the temporal edges in this portion of the list can extend a walk with a cost C1. Sorry, just 1 second. Okay, I'm back, sorry. So it means that all the temporal edges in this portion of the list can extend a walk with a cost C1, and they can extend a sigma 1 number of these walks with a cost C1. So what we can do here at this point is that as we are reading edge E and everything else has been computed for the first portion of the list, and this is sorted by arrival time, and E is here in this list, it means that basically all the edges preceding E, we have successfully, let's say, computed all the information needed about them, as they cannot be part of newly discovered walks in the remaining part of the computation, as they have a departure time which is less than the arrival time of E. So for this, we will assign, let's say, this information of the interval they belong here, and this will not be changed anymore in the computation. And we perform this up until E, which means that now we know the minimum cost of a walk that E can extend, and we know how many of the walks with this cost there are in the graph. So then, now that we know this information, we perform some operation on the list of temporal edges that departs from V, which is the head of E. So in that case, we also have this type of structure with the intervals, and we need to plug in the new information given by this edge E. So basically, we need to update these intervals. And here in this case, let's suppose that the cost of assigned to E was C2, which means that the cost of the walk ending with E, we also need to take into account E. So the cost of the walk ending with E is C2 plus the cost of E. And let's suppose that this cost, for example, is equal to C4 and greater to C3. So how do we update the information on these two intervals? And here, sorry, I forgot to mention that we need to take into account the window, let's say, of temporal edges that extend E. No? So here we are considering the one that departs from V, and we need to take into account the maximum waiting time constraints. So these from L to R are the temporal edges that depart after the arrival time of V, but before arrival time of V plus beta, which is the maximum waiting constraint. So here we are considering this window of edges, and we need to integrate the information in the intervals. So basically what we need to do is we need to update what concerns this last interval with a cost C4 and counting sigma 4. And as the cost is the same, we are basically enlarging the interval, and we are adding up to the number of walks that these edges can extend, the number of optimal walks that are brought to V through E. So here the counting will be now sigma 4 plus sigma 2, which are the number of walks, optimal walks ending with E. And here we also need to take into account this index LE, but we will see it in the next phase, why it's important. So after this first forward phase here, we managed to compute all the, for each temporal edge, we have the minimum cost of a walk ending with that edge, and how many of these walks there are in the graph. We have the count of this number of walks. So then let's see an intuition of what is the backward phase. And the backward phase is the phase where we need to actually compute the betweenness by bringing back the dependency of the edges. So here in this case, we are scanning ER in a backward phase, so by decreasing arrival time. And here, whenever we consider an edge E, we go and look at the list of temporal edges departing from B. And we have a variable, let's say delta V, that has the sum of the dependencies of the edges in a window of this list, which is defined by these two indexes here, LV, RV. And here, LE and RE are the successors of E in the optimal walks. So basically, we need to shift back this active window and update the sum of dependencies. So the temporal edges that are from RE to RV are not part anymore of the window that we are interested. So we basically need to remove the dependency given by these edges. And then we need to sum the edges of the edges that are newly part of the window. And then we update all the indices. So we can, once we do this operation, we can finally compute the betweenness of edge E from source S. Here, sigma SE is the number of optimal walks ending with E, and we can multiply it by the dependency computed in the previous step. And then whenever sigma star SE, which is, so here an important distinction is sigma is the number of walks that are optimal ending with E, and here are the number of walks that are optimal ending with E that are optimal as well for the node. Okay, so here it's only concerning the edge, and here the node as well. So whenever this is the case, we have to add to the betweenness also the contribution of this edge. So the way we handle these intervals, it's a bit involved, but the idea is here that we manage to perform all these operations in amortized linear time. And that's the way we need to be so careful in the way we update everything, which means that given a source node, we manage to compute the betweenness with respect to that source node in a linear time on the temporal edges. So then we have to repeat for each source node, and basically that's where comes the n factor in the complexity of the algorithm. So we can maybe now move to the experiment part. In this first part, we consider several temporal graphs. Here we have n is the number of vertices, m is the number of temporal edges, capital T is the number of time events, distinct time events. And here we are comparing ourselves with the previous algorithm in the literature, the one from KDD 2020. And so the algorithm that we propose is this one here, BCB. So here we have we used a Julia implementation. And the main takeaway here is that here in the last column we have the factor that we improved over the previous algorithm in terms of time computation, which we can see can range quite a lot, from 2 times to 250 almost. And then here on the same type of networks, we computed. So in this first case, in order to compare ourselves with the previous result, we have to consider shortest type of walks and no weighting constraints, because that was the setting for this algorithm in the literature. But whenever we set beta equal to infinity and we are considering shortest walks, this means that we are actually computing shortest path. So basically the result is indeed the same. We are computing the same objects. So the comparison is fair, let's say. While here in this second part, we are computing the temporal walks for different weighting restriction, different value of the maximum waiting time. Here it's expressed in seconds. So we have like 5 minutes, 10 minutes, and so on, and no weighting restriction. And we are computing the Kendall tau, which means we are measuring how much correlated are the measures, are 2 different measures. So for example, here FA, FO means that we are computing how much correlated are fastest and foremost, fastest and shortest, fastest and shortest fastest, and so on. And here we can see this pattern, let's say, where the measures are less correlated as we increase the waiting time constraint. It's probably the reason is that by increasing the waiting time constraints, we are less strict. So the number of temporal walks that we are considering is larger, and so then can be once the set is larger, they can be differentiated more the optimal walks with respect to different criteria. And then for the last part of the experiments, we perform some experiments on public transit networks. So we consider 6 cities with different sizes. And here we also reported small m. Small m is like the number of edges in the static graph that is the projection of the temporal graph. So it basically, yeah, if there is an arc, if there is at least a temporal edge connecting to nodes. And here we are comparing ourselves with Brandes. And as you can see, Brandes is much, much faster. But Brandes is performed on the static graph, where the temporal graph can be much bigger. But most importantly, what we noticed is that if, once again, we go and compare the betweenness obtained, for example, 2 different temporal betweennesses and a temporal betweenness with the static betweenness obtained by Brandes, we can see that the temporal betweennesses are much more correlated between them compared to how they are correlated with the static one. So this means that likely using Brandes on the static graph underneath a public transit network, it cannot be a useful proxy to measure temporal betweennesses. So finally, some open question and future work. Something that would be very interesting would be if we manage to find some conditional lower bounds, as we might think that NM is indeed kind of tight for the computation of temporal betweenness in this model. Then it would be interesting to study different centrality measures, for example, closeness. And finally, something that I would be particularly interested to is to make the model a bit more accurate in the case of modeling transport networks. So introducing footpath, which means arcs that are always available in the temporal graphs. And while the temporal edges are also enriched by some other fields like the trip ID. So it would be possible to let's say compute journeys instead of temporal walks, where you alternate taking vehicles like buses and walking, and it would be possible, for example, to measure the minimum number of transfers or this type of measures, of criteria for optimal walks. And that's it. And thank you very much for your attention.
Yeah, thanks for the great talk and yeah, the interesting problem. Do you think you can extend your do you think like how widely applicable like the problem is like more like in addition to the transportation domain, do you see like there may be some more applications of this in like biology or so on?
Of course, it can be applied to a variety of settings. I'm not so sure about the waiting time restriction of how many different settings that one is particularly interesting, like for sure transport networks we mentioned, but you also mentioned biology. I think there are some models where it's used to model like protein interaction. Temporal graphs are used to model protein interaction. Maybe even in that case could make sense to have a weighting restriction, but I'm not sure about that. But otherwise, without taking into account the weighting restriction, I would say that betweenness is a very general type of measure that can find application in all type of temporal networks. So
Exactly.
yes.
Yeah. Okay. Yeah, so thanks so much for the talk. If you have any questions, feel free to type in the chat or ask now or or email the speaker afterwards. Yeah, please go ahead, Julia.
I have a question on the future work. You mentioned the potential integration of footpaths. I think I did not understand your explanation. So you say the footpaths would be always available. Does that mean they would be available at each time step, or that there's no waiting time, or how do you mean
Yeah.
that?
So that would be a kind of a different type of model of temporal graphs. So
Hmm.
it would be a bit kind of a hybrid, because we would have these temporal edges that represent the connections of vehicles. So they are available at a certain time, and they take a certain time to traverse from stop to stop. And then footpaths would be like these edges that are always present, meaning that yes, we can say at each time step, for example, they are present, and they have always the same delay though. So that's kind of important, that they are always the same delay. So irrespective of time. Um, so there are some works already on, of course, on optimal work computation, let's say, in this type of setting. So where we have both type of edges, temporal edges, and these footpath edges, and you have to take them in combination. But I'm not aware of any work that consider this model for example, betweenness computation, or that also, because then things would become more tricky for sure. Like, are we computing only betweenness computation for temporal edges, or also for the footpaths themselves? So I think that there would definitely some work to be able to model this properly. But from an application point of view, then I think it becomes much more interesting, the type of result that we can get on transport networks, and they describe the reality quite more efficiently compared to just using the temporal connections, as is right now. I'm not sure if I answered.
Yes, yes.
Yeah.
Thank you. I understand now. Interesting.
Yeah. Yeah, so thanks for the discussion and the questions. Yeah, so we can, if there's no more questions, we can wrap up the talk here. So I think it's definitely a very interesting problem and have a different spin than kind of the normal temporal graph that we see, which just focus on the graph structure changes. So I think this notion of delay and the waiting time is like very interesting. So yeah, so thanks for sharing this topic with us, Filippo, and yeah,
Thank you very much. Thank
and have
you.
a great day, everyone. And we'll see you next week for the talk.